Welcome to the next lecture of linear algebra, Math 120. In the previous lecture, we were discussing the inverse of a matrix. Let me revise a couple of things about the inverse of a matrix. Let me adjust this thing first so that you can see the board completely. This one. We can only find the inverse of the square matrix. The first thing, the matrix should be square. Matrix should be square. The second thing, it is not always necessary that inverse of any square matrix exists. Okay, not always. The third thing is, let me see here. I had written here somewhere. We shall also discuss the properties of inverses. Properties of inverse of a matrix. Inverse of a. And how inverse? How to find inverse of any square matrix. By definition, if we have any matrix, this was the definition we discussed last time. If we have any matrix, let A be any n cross n matrix. N cross n matrix is a square matrix. Then a matrix B, a matrix B of same order is said to be inverse or inverse of A if A times B is equal to B times A is equal to IN, where IN is the identity matrix. This was the definition of. Then we say that if such matrix exists, then we say that B is basically inverse of A, and vice versa. And also A is inverse of B because of this definition. Means they both are inverse of each other. This was the basic definition of inverse of a matrix. Now, how to find inverse? How to find inverse of any matrix? Inverse of that matrix A, which we defined above, a n cross n matrix. A must be a square matrix. There are several methods. For example, first method which we are going to discuss is using elementary row operations. Finding inverse using elementary row operations. The second is by finding determinant and adjoint of a matrix. Determinant and adjoint of matrix A. So these are a couple of methods which we are going to discuss, how to find the inverse of a matrix. Why this is important, why we need to find the inverse of a matrix, because it helps us to find the solution of linear systems. Because I told you in earlier lecture that if we write linear system in this matrix form, then if we can find the inverse of a matrix, then X is, we can take A on the other side and we multiply it here. We can directly obtain the solution of a linear system by just multiplying the right-hand side vector and the inverse of a matrix. We'll directly get the solution of a matrix. Do you have voice problems? Can't you listen me properly?
Sir, we can, sir, we can, but there's a little bit distortion in your voice.
I think it's a system problem. I
Yes,
can't
sir.
do anything.
But I think जब आप walk कर रहे होते हैं ना तब होती है वैसे like अभी सही आ रही है. That's fine. वैसे.
How can I?
Sir, it's absolutely fine. Sir, it's absolutely fine.
If you have any issue, you can ask me to repeat that sentence or whatever. Okay, I'll repeat that sentence.
Thank you, sir.
Now let's have an example of finding inverse that we have by using first method, using row operations. Elementary row operations. We can use elementary row operations in order to find the inverse of a matrix. Let's have an example of this thing. Here we have an example. Let A be a 3 cross 3 matrix, 1, 2, 2, 3, 7, 9, -1, -4, and -7. So in order to find the inverse of this matrix, we write another matrix. For example, consider first you write the matrix A, which is given 3, 7, 9, -1, -4, -7. And then a vertical line just to differentiate between. So this is your A matrix. Now you write here an identity matrix of the same order as of A. A is a 3 cross 3 matrix here. So you write an identity matrix of 3 cross 3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. This thing. Now, after writing this matrix, you try to convert this matrix using elementary row operations. You try to reduce this matrix into identity matrix of order 3 by using elementary row operations. What you are going to do, you are going to transform this matrix into reduced echelon form. Okay. Which I hope you know what is reduced echelon form. We have already discussed a lot of things about reduced echelon form. In order to transform this matrix into reduced echelon form, the operations, the elementary row operations which you apply here on this matrix, you apply the same operations on this matrix as well. Okay. Then this matrix will be changed, will be converted from I3 to some other matrix. And that matrix will be your inverse of this A matrix. Okay, I hope you get it. Now let's do it properly. Let's apply elementary row operations on it and then get the inverse of A. Now, in order to reduce this matrix into reduced echelon form, what you have to do, first you have to make 1 here. So it's 1 already here. Now you are going to make zeros here below this 1. So what operations do I need here? -3 row 1 plus row 2. And this will change row 2. Okay. And this operation I'm going to apply in order to make zeros, 0 below this 1. Now, the first row will remain same. The second row will change. You multiply this thing with with -3, you get -3 here, -6, -6, -3. Okay, and then add in the second row. So what do we get here? 0, -5, +3, and then -3, 0. Sorry, not 0 here. 1, 0. So whatever operation you use here on this matrix, you apply the same operation here on this matrix as well. Okay, you just consider this is a matrix and you apply the usual row operations in order to reduce this left-hand portion into reduced echelon form. The third row will remain same, but we can apply two operations at the same time in order to save the time. So I'm going to apply another operation, which is row 1 plus row 3. Yes.
यहाँ पे सेकंड रो में 1 नहीं होगा, सेकंड रो सेकंड कॉलम यहाँ पे -5 लिखा है,
सेकंड रो सेकंड कॉलम यहाँ पे
हाँ 1 नहीं होगा,
अच्छा ये 7 है, it's 7, I think it's 1, so it should be 1 then. So -6, 7, 1, we get 1 here. Thank you. Now third row will also change. We are going to add first row into third row. We get 0 here, we get -2, and then -5, and then 1, 0, 0. Okay, now we get zeros here. Now the next thing is we have to make 1 here in the second row, the first non-zero entry. It's already 1. Now what we are going to do, we are going to make these two entries 0.
0.
Above and below this pivot entry 1. So I'm going to apply operation -2.
R2 plus R1.
Remember that we have to use only this pivot entry. So -R2 plus R1. This will
Into
change
R1.
row 1. And another operation we need here, 2R2 plus R3. And this will change the row 3. Now tell me the resulting matrix. Complete matrix.
So 180 into 1, 0 into 1. Okay, so 1, sir, at the top 1.
The top 1, yes. We
0,
must get 0 here, 0 here,
3
0
into
here.
4, 3 into 4. Sir, -4.
-4,
3 into, sir, 7.
7, and then
Sir, -2.
-2, and then 0.
Then 0. Yes, sir.
Okay. The second row
And-
would remain same.
-3, 1, 0. And sir, the third will be not be 0. It will be -2.
This one?
No, sir, the right one. The right one.
This one?
Yes, sir. No, sir, the middle
Minus-
0. Sir, the middle 0. Sir,
It's
I'm talking
negative.
about the middle. Sir, I'm talking about the middle 0 in the third row.
This one?
Yes, sir. It should be -2.
No, I'm applying the second operation again as well on the same matrix. So it must be 0 then. See? I told you we can apply multiple row operations on the same matrix. But
ऊपर जो पहले वाला था उसके थर्ड रो के आखिरी एलिमेंट में 1 नहीं आना चाहिए
1,
Yeah.
sir.
ऊपर वाले में जो ऊपर है जो बोर्ड के ऊपर है टॉप लेफ्ट साइड पे ये वाला और यहाँ पर
you
third row
tell me
के-
about this matrix. Tell me the entries of this matrix.
Okay, sir. Okay, sir. Okay, sir. 0, 0, 1, 0, 0, 1.
Last time? Last
Yes,
time?
sir. Yes,
0,
sir.
0, 1,
-5,
-5,
-5, 2,
2,
and 1.
1. Okay. So this is what we have obtained here. Now in the third row, we have to make 1 here, which is fortunately already 1. So now we are going to make zeros, these entries 0. Okay.
Oh,
By
1,
applying
2, 3,
row
3.
operation.
लास्ट में 0 नहीं होगा, लास्ट रो में एंड पे -5 2 के बाद 0
यहाँ पे 0,
ऊपर तो
सर
0 है
1
ना,
नहीं होगा. सर 1
1
नहीं
होगा.
होगा. 1 होगा.
यार यहाँ पे ऑलरेडी 1 नहीं होगा यहाँ पे.
Yes, sir. इधर 1 है.
यही
हाँ,
यही
तो
कह
one
रहा था मैं पहले
हाँ, this was 1, and now here, what do you have here?
सर इधर 1 नहीं होगा. मैंने आपको सही
चलो.
बताया. 0 plus 1 is 1.
ठीक है, ठीक है, ठीक है, ठीक है. Now, what operations do we need here in order to make these two entries 0? So you have to use only this pivot entry. So it is -3 row 3 plus row 2, and this will change your row 2. And the second operation which we need here, 4 row 3 plus row 1, and this will change row 1. Now apply these two operations, and
3 into 0 into
so,
0.
so we must get 0, 0, 0, 1, 0, 0, 0, 1. Now tell me this matrix.
Sir, right. Sir, please write. -13,
-13,
6,
6,
and 4,
4,
and 12.
12,
1. Sir, -5,
-5,
0 into 1. Sir, -3.
3,
Sir, -5
-5,
and 2.
2, and 1.
Answer 1.
Because R3 is not
Yeah,
going,
yeah,
R3 is not
yes,
going to
sir.
change.
Yes, sir.
Now, you can see here that original matrix has been transformed into identity matrix. This is your identity matrix of order 3. And same operations have converted the given identity matrix into some other matrix, which is the inverse of the given matrix. You can check this. You can check this out, whether this is correct or not. This is your A inverse. A inverse is what it is. -13, 6, 4, 12, -5, -3, -5 to 1. Now, how can we check it? You just multiply A and A inverse. You should get identity matrix of order 3. Or you can multiply A inverse and A. You should again get the identity matrix of order 3. So this is basically a kind of verification. We can verify in this way that whether we have find the correct inverse of the given matrix or not. If you have any question, you can ask me. There are questions in the chat window. Let me. If you have any question, you can ask me. Now, what if the inverse of a matrix does not exist? In that situation, for example, what do we obtain here if there is no, or the inverse of matrix does not exist? Then,
Sir, if the inverse of the matrix doesn't exist, then we are not going to obtain an identity matrix over here.
yes, that's obvious. If we do not obtain identity matrix here on the left hand side, or you can say that if the given matrix cannot be converted into identity matrix after applying series of row operations, then the inverse of the given matrix does not exist. For example, if we obtain here 0 here, 0, then this is not an identity matrix. Then this will not be inverse of the given matrix as well. Okay. The left-hand matrix should be exactly as the identity matrix of same order. So this is basically, this is how you can say that inverse does not exist in this case. There is a question in the chat window. It's a good question. Sir, is it possible that AB is equal to I, but BA is not equal to I? If so, what is this case called? It is called nothing. In that case, you just say the inverse of A does not exist. But if the given matrix has been converted into identity matrix, then these two products, A into B and B into A, must be equal to identity matrix of order 3, because in that case the inverse of a matrix must exist.
Sir, is there any possibility that A into A inverse, we like get that identity matrix, but while doing this A inverse and A, we don't get it?
I told you already, if the given matrix has been converted into identity matrix, then these two products must be equal to identity. Okay. Then A into A inverse and A inverse into A, they must be equal to identity matrix of order of the same order as of A.
Right, sir.
Okay. So this is how you can find the inverse of a matrix. Now this method can be applied on a matrix of any order, whether the order of a matrix is 5 by 5, 10 by 10, or any other. So you can have practice exercises. I usually write the exercises for practice at the end of the slides. You can see there and practice them. I told you already upper triangular matrices, lower triangular matrices, transpose, and these things. Now, let us discuss again a little about the linear system. As I have told you, that if we have any linear system, for example, you need to solve this linear system. Solve the linear system. This one, x1 plus 4x3
Excuse me,
is
sir.
equal to G, beta.
Sir, we just wrote right now that under the heading that how to find the inverse of A, the first one saying that using elementary row operations, and we also wrote a second category
Yes.
using determinant.
Yes. We are going to discuss that category after discussing this thing.
Okay, sir.
Okay. I'm just going to tell you how to solve the linear system by finding A inverse. Now you can see that this is your linear system. You can write the corresponding matrix form of this linear system. 2, 0, 1, 1, 0, 4, 2, negative 1, 5, 2, negative 2, and negative 7. So this time, so you must have x1, x2, x3 here, and the right-hand side vector, 13, 3.5, and negative 19. Okay. Now this is your A matrix. Okay. This is your A matrix. You just find the inverse of this matrix by using these elementary row operations separately. If the inverse of that matrix exists, then you can write. Then you can write that linear system in this form. You can multiply A inverse on both sides from the left-hand side. Now, this A inverse into A is what? It is identity matrix, okay, of the same order. If this matrix is of order 3 cross 3, then this is identity matrix times X is equal to A times A inverse times B. So X is equal to A inverse times B. So this is in fact your solution.
वो
So-
इब्राहिम का क्या बना क्लास ले रहा है मेरे साथ मुझे कोई पता नहीं
Kindly mute your mic. Was talking to someone, I think. So you have to find the inverse of this matrix, and then you have to basically multiply this inverse with B, and you obtain the solution. This method is applicable only if the inverse of matrix exists. Otherwise, we cannot apply this. Okay, this method.
सर एक क्वेश्चन है सर जो हम रो एशेलॉन फॉर्म में कन्वर्ट करते थे और फिर सॉल्यूशन फाइंड करते थे वो उस केस में भी एप्लीकेबल हो जाता है जब मैट्रिक्स का इनवर्स ना भी एग्जिस्ट कर रहा हो तब भी हम उस मेथड से फाइंड आउट कर सकते हैं
if that matrix is a square matrix, if the inverse of that matrix exists, ठीक है
नहीं ये तो हम आइडेंटिटी में लाइक सर जो हम पहले करते थे हम वो रिड्यूस्ड रो एशेलॉन फॉर्म में करते थे और फिर हम उधर से फाइंड आउट करते थे सॉल्यूशन तो उस केस में तो मैट्रिक्स का इनवर्स होना जरूरी होता था या नहीं होता था
नहीं in that case that is a more general method than this
हाँ वो अगर किसी मैट्रिक्स का इनवर्स नहीं एग्जिस्ट करता तो उस पे भी हम वो लगा सकते हैं
हाँ वो तो डिफरेंट मेथड था ना वो तो हम augmented matrix कैलकुलेट करते थे augmented matrix लिखते थे and then we try to reduce that whole augmented matrix into echelon or reduced echelon form and then writing back the linear systems we use either backward substitution or we get directly the solutions. Okay? This method is slightly different. In this case, this method is possible only if A inverse exists. Okay? Otherwise, you cannot transform, you cannot convert or transform this matrix. You cannot bring this matrix on the other side. Okay. If A inverse exists. This is possible only when A inverse exists, then we can write A inverse into A's identity matrix. Otherwise, no. I told you here. If A inverse does not exist, then this is not true. Okay. If A inverse exists, then this is true. We can write here A inverse into A identity, and identity into any vector or matrix, it gives us the same vector or matrix. Okay. So in this way, we can find the solution. Then by multiplying these two matrices, we can obtain the solution directly. So that's why I have written here, this method is possible only A inverse exists. Otherwise, no, we cannot use this method. The method which we have already discussed earlier, that is more general than this method. Okay. If you have any other question, you can ask me. There are a couple of theorems which we need to discuss here only, but I'm not going to prove these theorems here. You have to remember these things. So there are a couple of theorems which we need to discuss here. If A is a square matrix, if A is a square matrix of order n, n could be any order, then the following statements are equivalent. Then the following statements are equivalent. Number one, A is invertible. Second, A x is equal to 0 has only a trivial solution. Third, reduced row echelon form of A is identity. The reduced row echelon form of A is IN. Now, in this theorem, the three statements are equivalent. What does it mean? In any theorem, if you see whether the following statements are equivalent, it means that if at least one of these statements is true, if you can prove it, then you don't need to prove the others. The others must be true. If at least one statement is wrong, then all other statements must be wrong. That's why we call them equivalent statements. Okay. So the following statements are equivalent means if one of these three is true, then other two must be true. So if A is invertible, what does it mean? A inverse exists. Okay. If A inverse exists, then this homogeneous linear system AX is equal to 0. It must have only the trivial solution, only one solution, which is 0 solution. And the third one is the reduced row echelon form of that A must be equal to the identity matrix. Okay, so that's what we have proved there a couple of moments ago. The given matrix A was invertible, so that matrix has been converted into the identity matrix of order 3. And if the A inverse exists, or if A is invertible, then obviously this matrix, when we take this matrix on the other side, then obviously we get A inverse times 0, So anything multiplied by a zero vector must be a zero vector. So this statement is again true. Okay. So these three statements are.
Sir, can I ask a question?
Ji.
Sir, A is a square matrix. That makes sense. But is it necessary that every time a square A matrix will have an inverse?
Written at the start of the lecture, I told you that it is not necessary always that any square matrix has inverse. Okay. For example, I'm going to write here a matrix. This one, check it yourself. 1, 2, 2, 1, 3, maybe 4, and 2, 4, 4. This matrix is not invertible. How do I know? How can I write? Because you can see that the row 3 and row 1,
is a
they are multiple of
two.
each other. Okay?
Yes, sir.
Row 3 is a multiple of multiple of 2 of row 1. So whenever we are going to make this thing 0, okay, the reduced echelon form of this matrix will have the last row completely 0. Now, whatever here you have identity matrix, if you get the last row 0, then this matrix is not invertible, even it is a square matrix. Okay? I hope you get it.
Yes, sir.
By this theorem, you can say that this matrix is not invertible because it cannot be converted into identity matrix. Another statement is that if A is invertible, then the fourth statement of this theorem, for each n cross 1 matrix B, the system of linear equations or equations AX is equal to B has exactly one solution. Exactly one solution, or you can say that the unique solution. Okay, exactly one solution, or you can say unique solution. Okay, why this is so? Because whenever this matrix A is invertible, you can take that matrix on the other side and you can write A inverse into B. Okay, now whatever the value of B is, whatever the value of B here is, you will get A inverse into B only one solution. Okay, only one solution for any particular value of B, whatever the B vector is. If you change this vector, then the solution will be changed. That's why here it is written for each matrix B, the system of equation has a unique solution. Okay, you cannot have infinite many solutions if the coefficient matrix is invertible of any linear system. You will definitely get the unique solution.
Sir, can you explain the point 4 again?
Point 4 again. Again, if the coefficient matrix of any linear system, if this is your linear system, whatever the value of B is, the right hand side vector, it should be non-zero. If it is 0, the right hand side vector, then we have the second statement. Okay, then we will have homogeneous linear system. So this B should not be 0. B vector should not be 0. Okay, right hand side vector. Now, if this coefficient matrix is invertible, then this linear system must have unique solution. Okay. We cannot have infinite many solutions for these kind of linear systems whose coefficient matrix is invertible matrix. They'll have unique solution. Only one solution.
Sir, n times 1 जो है हमेशा ये invertible है.
M? What did you say?
N times 1. सर ये ऊपर जो आपने लिखा हुआ है for each n times 1.
N times 1 matrix B, this is the right hand side vector. I'm defining
Yes.
that vector, okay?
Achha.
Because A is a square matrix of order n. So this is your matrix n cross n times x is equal to B. B vector should be n cross 1. Similarly, x vector should be n cross 1 as well. So that the multiplication is possible.
ठीक है.
Okay. The right hand side, whatever the right hand side vector is for each means whatever you can change the value of B as well. Whatever the value of B is, this linear system will have a unique solution if the coefficient matrix is invertible. And this is only possible when the A matrix is a square matrix. Okay. For rectangular matrices, we cannot apply this theorem or this statement. This is the fourth statement, which must be true if at least one of these four statements. If at least one of these four statements is true, then all other statements must be true. If you have any question, you can ask me. In the context of this statement, there is an example which let me discuss with you people.
Sir, I have a question.
जी बेटा बोलो.
One thing again.
जी बोले.
Can you please explain the n into 1 thing again?
It's a vector. It's the order of that vector. ठीक है. हमने यहाँ पे क्या लिखा? If A is a matrix, is square matrix of order n. Basically क्या है? A का order n cross n है. ठीक है. तो ये B का order क्या है? B का order क्या होना चाहिए? N cross 1 because it's a vector. Vector किस टाइप का है? B1, B2, so on, Bn. इसमें कितनी rows हैं? N rows हैं और 1 column है. So this is what we call B vector. You got it, or do you still have any confusion?
I got it. Thank you.
Okay. Now, there is an example in the context of the last statement. If we have this linear system, for example, we need to solve it. X1 plus X2 plus 2X3 is equal to B1. And X1 plus X3 is equal to B2. And 2X1 plus 2X2 plus 3X3 is equal to B3. What conditions must B1, B2, and B3 satisfy in order for the linear system to be consistent? So we need to find here some conditions on this right hand side vector. Okay, now if you try to write this matrix into augmented matrix, if you try to write the augmented matrix corresponding to this, to B1, 1, 0, 1, B2, 2, 1, 3, and B3. Okay, this is the corresponding augmented matrix. You can write A, B here. Now, if you want to find some conditions which these B1, B2, B3 must satisfy in order for this linear system to be consistent, what you have to do. Again, for example, if someone asks you, if I ask you, prove that this linear system is consistent, what you do? Okay. This is आप इसको आप second question कह लें. First question जो है, prove that here ये check कर ले. Check whether the given linear system is consistent for all B vector. ठीक है. अगर आपने ये check करना है, then you can use that statement which we have discussed, the fourth statement. If the coefficient matrix of this linear system, the coefficient matrix is what? It is 1, 1, 2, and 1, 0, 1, 2, 1, 3 times x1, x2, x3 is equal to b1, b2, b3. Now, I'm asking you whether this linear system is consistent or not. What you are going to do here, you only check whether this coefficient matrix A, for this A is invertible. You check only this in order to check whether this system is consistent or not. Means if it has a solution or not. Then you just need to check A is invertible or not. Now, can you guys check whether this is invertible or not? You have to find A inverse. Okay, let me see whether its inverse exists or not. So the inverse of this matrix does not exist, because whenever we try to solve this, whenever we try to find the inverse of this matrix, one row of this matrix has been converted into 0. Let me show you what we have obtained. The row 1, 1, 2, 0, 1, 1, 0, 0, 0. Whatever the I is here. Now this matrix is not invertible. You can see here that one row is 0. So it means A inverse does not exist. What does it mean? It means that this linear system might not be consistent. Okay. Now, the second question is, under what conditions must B1, B2, B3 satisfy so that the given linear system becomes consistent? Okay. In that case, we are going to write the corresponding augmented matrix of corresponding to the given linear system and try to reduce it into reduced echelon form. Now, you can see that this matrix can be converted into the matrix which I have written here. This one, it's a similar kind of matrix. This, after applying row operations, we have obtained 1, 1, 2, 0, 1, 1, 0, 0, 0. Here we have B1 on the right-hand side vector, B1 minus B2, B3 minus B2 minus B1. So this is what we have obtained. Now, what should be the condition on B's so that this linear system becomes consistent? What it should be in your view? Kindly tell me. Anyone? There's a question in the chat window. Anyone tell me what conditions should we impose here in order to get?
B3 should be a sum of B2 and B1.
Yes. Means in short, if this row is 0, the last row is 0, then the right-hand side must also be 0. Otherwise, you will have inconsistent system. So this right-hand side thing must be zero, sorry, must be zero as well in order to get the consistent linear system, in order to get at least one solution. So this B3 should be equal to B1 plus B2. So this is the condition which B1, B2, and B3 satisfy so that this linear system will become a consistent linear system. I hope you get it.
Sir, a
Ji.
side question. Sir, if
Ji, ji.
this bottom B3 minus B2 minus B1 is not equal to 0, then this particular linear system will have infinitely many solutions?
No, it will have no solution. It will be inconsistent. In this case, it will have infinite many solutions.
Okay.
Okay.
Thank you, sir.
तो ये आपने मैट्रिक्स पे राइट साइड पे B1 माइनस B2 B1 माइनस B2 B माइनस B3 ये किस बेसिस पे लिखा है?
क्यों लिखा? ये जो ऑगमेंटेड मैट्रिक्स है ना, शुरू में जो लिखा था कॉरेस्पॉन्डिंग टू लीनियर सिस्टम, उस पे हमने रो ऑपरेशंस लगाए और इसको हमने we have tried to reduce this augmented matrix into reduced echelon form. Okay. After applying series of row operations, we have reached here. क्योंकि जब आप रो ऑपरेशन इधर लगाएंगे तो इस 20 पे भी तो लगाएंगे ना, क्योंकि ये आपका राइट हैंड साइड वेक्टर है, तो 20 पे लगाएंगे तो आपके पास इस तरह की चीज आ जाएगी. आई होप यू गेट इट. You got my point? Okay. After applying row operations, you have reached here. ठीक है. अब आपने यहाँ पे जीरो करना था ना, ये आपका पिवट एलिमेंट है सेकंड में, आपने नीचे जीरो और ऊपर जीरो करना था. ठीक है, नीचे जीरो आ गया लेकिन ये भी जीरो हो गया. So we stop here because we get a very strange row, which is this row, because it contains all the zeros on this left hand side and right hand side here. In the start of linear systems, when we try to solve these linear systems, I told you this situation arises when the system is not consistent. Okay, this is consistent only if this thing must be equal to 0. Otherwise, the given linear system is inconsistent linear system. From here, we can find that condition. देखिए, अगर B3, B1 और B2 के इक्वल होगा तो आपके पास यहाँ पे क्या आ जाएगा? 0 आ जाएगा. ठीक है. अगर यहाँ पे 0 आता है तो फिर आपका जो सिस्टम है गिवन वो कंसिस्टेंट लीनियर सिस्टम होगा. आई होप यू गेट इट. अदर थिंग, अगर हम B1, B2, B3 को अगर हम वेक्टर की फॉर्म में लिखना चाहें, जैसे कि ये हमने राइट हैंड साइड वेक्टर था ना ये वाला, ठीक है, तो इस केस में क्या होगा? B1, B2 और B1 plus B2. Okay, and this can further be written as B1 times 1, 0, 1 plus B2 times 0, 1, 1. Okay, it means कि आपका ये वाला जो वेक्टर है B1, B2, B3, that vector should be a linear combination, means it should be a combination of you can say the products and sum of these two vectors, 1, 0, 1, 0 and 1, 0, 0. ठीक है. You can write that vector. If you have any question, you can ask me. There are some exercises which I have given on slide 25. You can see these exercises and try to solve them by using this method, by finding the A inverse. Now, let's get back to the method for finding A inverse. The first method which we usually use in order to find A inverse is this method which we have just discussed, by using elementary row operations. Now the second method, yes.
So will we ever asked to use a particular method for finding the inverse of anything, or it's a choice?
Yes, I might ask you to find a particular method for finding A inverse. Okay, if it is not given, you can use any method. Okay. Now, finding A inverse by finding determinants and adjoint matrix, or you can say the cofactors and many other things. Now, if we have a 2 cross 2 matrix, okay, for example, A is a 2 cross 2 matrix, for example, 1, maybe -3, and 2, and 4, okay? If this is a 2 cross 2 matrix, then I hope you already know how to find inverse of that matrix. Inverse of this matrix is what? What over 1 over determinant of A times adjoint of A. And that matrix, that is what? In fact, adjoint of A is a matrix. You don't need to put here, again, the capital brackets. Now, what is this? First, you need to find the determinant of A. Determinant of A is denoted by either determinant of A, or you can denote the determinant of Y in this using this notation by putting 2 bars on either side. So it is what? It is again denoted by 1, -3, 2, 4 by vertical, putting a vertical bars around that matrix. Now, this is the notation of a determinant, and this is a notation of a matrix. Remember this. Now, how do we find determinant of 2 cross 2 matrix? We multiply these two numbers which are in the diagonal, 1 into 4, minus the numbers in the off diagonal, okay, which is 2 into -3. This is how we find the determinant, and which is 4, negative, positive 6, and which is this is 10. Okay, this is how you find the determinant of 2 cross 2 matrix. So this determinant should not be equal to 0. If it is 0, then this determinant, it is in the denominator. It should not be 0. If it is 0, then you cannot find A inverse. Okay, because you'll have infinity here, and anything multiplied by infinity is infinity. So now, what is the adjoint matrix? Adjoint of A is what? Is the same matrix, but you have to replace the positions of elements in the diagonal 4, 1, and the signs of elements of the off diagonal elements. This is how you find the adjoint of any matrix. Now, once you have adjoint, you can find A inverse is equal to 1 over determinant times adjoint. It is 4, 3, -2, 1. After solving this, means it is 2 by 5, 3 by 10, -1 by 5, and 1 by 10. This is your A inverse. Okay. Now, how can you check whether this is a true A inverse of the given matrix? You can multiply A into A inverse. You should get A identity matrix of order 2 either, or you multiply A inverse with A and you get identity again of order 2. Yes. So this is the basic definition. Now we are going to generalize these things for the matrices of higher order. Means 3 cross 3 matrix, 4 cross 4, 5 by 5 cross 5, or 10 cross 10, or whatever. Now, in order to generalize this definition for higher order matrices, first we need to generalize this definition of determinant. How to find determinant of matrices of higher order, 3 cross 3, 5 cross 5, 10 cross 10, and so on. Okay, if you have any question, you can ask me. So these are equivalent statement about any square invertible matrix. A is invertible, then A, we call it A is non-singular. We call also A inverse exists, and also determinant of A is not 0. Number 5, A can be, sorry, the reduced echelon form, जो कि पहले हमने लिखा था, reduced row echelon form of A is identity matrix of the same order. Okay, so all these statements are, in fact, they are equivalent. Okay, A is invertible, A is non-singular, A inverse exists, determinant of A is not 0. The row reduced echelon form of A is always identity matrix. If at least one of these statements is true, then all these statements are, they must be true. Okay. Now, what is the general method of finding A inverse? It is 1 over determinant of A times adjoint of A. Okay, so it's easy to find A inverse for 2 cross 2 matrices, but for higher order matrices, this method is very lengthy, and we'll discuss it. We don't basically use these kind of methods in practical situations. This is just a method. Just you should have information about it. Now, but first thing you need to find is determinant of A. Here, determinant of A. How do you find determinants of any matrices when the matrix order is higher than 3, 4, 5, 6, and 10? First, we are going to discuss, we are going to discuss different methods of finding determinant of A. Okay. So determinants. Determinant of any matrix can be calculated using cofactor expansions, and that is so one thing you should know that determinants can only be found of square matrices, not of rectangular matrices. The matrix should be square. Okay, this is the mandatory condition. Now, how to find determinants using cofactor expansions? This is what we are going to discuss now. First method, finding determinants using cofactor expansions. Number one method. The second is we can also use the elementary row operations to find the determinants of any given matrix. But the elementary row operations in this case would be slightly different than the usual elementary row operations which we have discussed earlier. Okay, the first method which we are going to discuss is the using cofactor expansions. Now, for example, if we have any matrix of order n cross n, and its entries are A11, A12, so on, A1n, and A21, A22, so on, A2n, and so on, AN1, AN2, so on, ANN, and so on. Okay. So this is your given matrix A, whose order is, you can see that its order is n cross n. Order is n cross n. Now, what is the minor of a matrix? We need a couple of basic definitions in order to define this cofactor expansion method. We are going to discuss those basic definitions. Minors of a matrix. What is a minor of a matrix? Minor of a matrix. The first definition. Minor of any matrix A corresponding to some of its element. Okay, this is a matrix, and these are elements of the matrix or entries of the matrix. Okay. We define minus Mij. Okay. Mij आप कह सकते हैं the minor Mij of any element Aij, okay, of the any corresponding element, आप कह सकते हैं of any corresponding element Aij of A is defined as या इसको define न करें, is a matrix of order n-1 cross n-1 obtained by deleting or eliminating ith row, eliminating इसके बाद इस तरफ में लिखा हूं यहाँ पे, by eliminating ith row and jth column of the matrix A. I hope you get it. Read it again. The minor Mij of any element Aij of the matrix, of the given matrix A, is a matrix of order 1 less, n-1 cross n-1, which is obtained by deleting or eliminating. In fact, deleting, not eliminating. We are not, this will confuse you. By deleting ith row and jth column of the given matrix A. Let's discuss this with the help of example. Okay. For example, if you are, if we are given a matrix of 3 cross 3 or 4 cross 4 or any order matrix. For example, A is a matrix of order 1, 2, 3, 4, minus 4, 3, 0, 1, 8, 9, 2, 1, minus 1, and 0, 2, 7, 9. So this is your matrix. Now, what will be M11? M11 is in fact a matrix of order. इसको order क्या है? 4 cross 4. Okay, it's a square matrix. Then M11 is what? 1, 1. This is your row, and this is your column, which you are going to delete. First row and first column. First row and first column. You delete these two things and write the rest of the thing. So this is your M1, minor M11. Okay, I hope you get it. Now, if you want to write a minor, maybe minor 2, 3, what will be this matrix? You are going to delete second row and third column. Okay, second row and third column. You are going to delete these two things from the matrix A, original matrix. Second row is what? This is your second row, and you are going to delete the third column. Rest of the entries you write in this matrix, which is 1, 2, 4, 8, 9, -1, 0, 2, 9. Okay, so this is the minor 2, 3. Similarly, you can find all the minors. Okay, similarly, you can find all the minors M11, M12, M13, and so on, all the minors. In fact, M44, and so on. Okay. This is the first basic definition which we need to define in order to discuss that method using cofactor expansion. The second thing which we need to define is the cofactors of A. The second definition which we need is cofactors. Any cofactor is defined by ij, and it is -1 power I plus j. Cofactor corresponding to some entry of the matrix is defined by Cij is equal to -1 power I plus j times the minor corresponding to that entry, Mij. This is what we call cofactors.
Excuse me, sir.
Cofactor, जी बेटा.
सर अभी हम कुछ लोगों की लैब शुरू होने वाली है और कैंपस में हमें मतलब जाना भी पड़ेगा.
कितना बजे? 12:30 बजे क्लास शुरू होती है ना यार.
जी सर.
We have still 5 minutes to finish this class. Huh? Cofactor, you can say of Aij corresponding to, या आप कह सकते हैं cofactor corresponding to Aij, that would be better, corresponding to Aij. Okay. If you have any element Aij, then its corresponding cofactor Cij is defined to be -1 power I plus j times minor ij, Mij. You can find all the cofactors of the corresponding to that matrix. For example, C11 is what? It is -1 power 1 plus 1 times M11. Okay. Similarly, you can find C12, which is -1 power 1 plus 2, M12. Okay. M11 corresponding to that matrix we have calculated it. Here it was basically M11. This is your A matrix. This is your M11. So 30192 -1271. In fact, one thing which I missed here, it is basically here determinant of Mij. I think this is the proper definition. Yes. Or in the minor as well, you have determinant, not the matrix. So what this means, basically here, in minor, you must have determinant here, not the simple matrix. This is the minor. It's just determinant, M11. Here, you also must have determinant of this matrix.
So what do you mean by determinant? Do we have to find the determinant of this matrix which you have written 392027?
Yes. Cofactors are basically what? They are determinant of minors, or directly you can write here determinant of Mij. Okay, or you can determinant of Mij as minors. So M11 is what? It is -1 power 1 plus 1 times determinant of what? Mij. Mij is what? 30192 minus 1. It is 30192 minus 1 and 279. So this is your M11. Similarly, you can find C12, it is -1 power 1 plus 2 times that matrix, determinant of that matrix. Okay. Similarly, you can calculate 13, C14, and so on. The last one is C44. Okay.
So in order to find this cofactor, we have to multiply this expression -1 square with the determinant of the particular, which like
Yes,
C1.
corresponding minor.
Oh, okay. So this is not an absolute final answer.
Not yet. So we after finding these cofactors, which are some real numbers, you find the matrix of cofactors. Okay? You find the matrix of cofactor, which is of same order as of A. Okay? So the matrix of cofactors, yeah, cofactors matrix. Cofactor matrix. It is usually denoted by C, and you can say it as C11, C12, C13, C14, corresponding to the given 4x4 matrix. So you'll have C21, C22, C23, C24, and then C31, C31, C32, C33, C34, and the last one is C41, C42, C43, and C44. So this is your matrix of cofactor. Now, the transpose of this matrix is basically adjoined. What you say, take care. Adjoint of C is what? It is C transpose. Okay. Now, the inverse of that matrix is what? 1 over determinant of A times, you can say adjoint of A. You can say adjoint of A is basically C transpose. So now inverse A inverse is equal to 1 over determinant of A and adjoint of A. Now this first, you can use the same formula in order to find the inverse of that matrix A, whatever the order is of that matrix given. Okay, so that is basically a very long procedure of finding A inverse using cofactors.
Sir, given with this particular given formula for A inverse, we can also make it like 1 over determinant of A into the transpose of C.
Huh?
1 over determinant of A into transpose of C.
1 over determinant of A into transpose of C. Yes. That is the method of finding A inverse. Okay. We haven't discussed further the determinant of how to find the determinant. This is what we call the method of finding A inverse. But how to find this determinant? Okay. ये तो मैंने आपको शॉर्ट में बता दिया कि इन्वर्स कैसे फाइंड करते हैं by finding cofactors. Okay. Now let's get back to the determinants. How to find the determinant? This is what we call the minor. And now cofactor expansions. उसको हम दोबारा डिस्कस करेंगे. We'll do an example of that thing. Okay. Now the cofactors आपने देख लिया. Now cofactor expansions. Cofactor expansions.
1 मिनट ऊपर हो गए.
Expansions
लैब जब भी जाना है सर.
to find, okay, to find determinant. Okay. We'll start next lecture with this thing, cofactor expansions for finding determinant of a matrix. I think we should stop today here. If you have any question, you can ask me.
Yes, sir. So the question is that we have used this the matrix A to find a minor, which is minor 1, 1. Why can't we take another minor by eliminating a row and a column from this minor, particularly this minor M1, 1, in order to make it a 2 by 2 matrix, and then using that 2 by 2 matrix, we find the determinant of that matrix, and that will be for the entire matrix.
Yes, we are going to do this one. We are going to do this thing to find the determinant of a matrix. Otherwise, it is not possible.
Yeah. Yes, sir.
We'll find these minors until these minors will reach at 2 by 2 matrix. Okay. Otherwise, we cannot find determinant of 3 cross 3 matrix. This which is M11. We don't have any method to find this determinant. So
yes,
once we have obtained one minor, then we have to reduce it into another minor, which is 2 by 2, by eliminating first row, first column, or second row, second column, or
Yes,
whatever.
sir.
We are going to discuss it in more detail when we are going to discuss cofactor expansions to find the determinants. Okay.
Yes, sir. My instinct
the-
was saying that this is the only method of solving this.
Yes. Yeah. What
Yes,
did you
sir.
say?
So I was saying my instinct was telling me that this is going to be
Yeah.
the absolute answer,
Yes.
the method of doing this.
So because this is going to work, but it is a very lengthy method. We don't use this method when we have a large matrices of order, maybe 5 cross 5 or 10 cross 10. This will take a lot of time. We'll discuss another method, which is by using elementary row operations in order to find the determinant of matrix. That is more practical and is more implementable, you can say, in computers.
Yes, sir.
Okay.
सर यहाँ पे जो माइनर है वो मैट्रिक्स है या डिटर्मिनेंट है, ये मुझे समझ नहीं आई.
It's basically
The minor एक वैल्यू है या मैट्रिक्स है, मुझे
it's basically, you can say it's a matrix. Okay, it's a matrix. But in the cofactors, you have to take the determinant of this thing. Okay? That's why I have written here Cij is -1 power I plus j, determinant of that minus. So the minus should be a matrix. That's why we can take a determinant here. I hope I'll clear you this confusion in the next lecture. If I don't exactly remember, you can check in the book as well. What exact notation do they use for these minors and cofactors? In the next lecture, I'll clear this thing.